All right, guys, there we are going to consider our question paper, which we wrote in March, that is from the April exams that we are given. So we are going to quickly rush through our questions and see how you're supposed to attempt these typical questions. So make sure that you go through your instructions, the answers to 3 decimal places. And also on question number 7, use pi to be 3,142. All right, that's something that I don't even consider, but it's an instruction that you can also put into consideration. All right, question number 1, various options are given as possible answers to the following questions. Choose the answer and write only the letter A to D next to the question number. That is what you're given for these first 5 questions that we are given. You are supposed to indicate the answer that is given. So they were given which is not an advantage of using a bridge rectifier is not an advantage, meaning to say that is not part of a rectifier, okay, a bridge rectifier, rather than a 2-diode full rectifier. All right, so it is not small, it is lighter, it is more efficient design, it costs less. So we know that this one, it is actually cost, it is expensive. This is not an advantage, this one. It is advantage to a 2-diode, not from a bridge rectifier. So that is, we are not having this. So this is not an advantage at all. All right, 1.12. We are given which diode is optimized for operation in breakdown region and is often used as a voltage regulator. So remember, that's a Zener diode which we use for the breakdown, and also it is used as a voltage regulator. That's a Zener diode. When transistors are used in digital circuits, they usually operate in them when transistors are used. So transistors, they operate in this region, the saturation and cut-off regions. When they are used in digital circuits, they will be in saturation and cut-off regions. So remember, guys, to just go through your theory that can also help. In a common emitter configuration, an emitter resistor is used for what? All right, so this is used for what we call the collector bias. That is used for a collector bias. Transistors may be used as switching devices or as they are also transistors, fixed resistor. No, this is not a rectifier. No, they can be a variable resistor. Transistors can be used for the variable resistor. We can have that rectifier. No, a rectifier, we are having diode there. Diode, not a fixed resistor. No, it cannot be a fixed resistor. So the best answer there was going to be the D. Okay, so this is operational, the applications of a transistor. 1.21, we are given indicate by false, true or false. A semiconductor is a material that is neither good conductor nor a good insulator. A semiconductor, that is actually true. This is the definition of a semiconductor. The sharing of valence electrons is called covalent bonding. That is also true. We talked about this. The avalanche is the effect that causes a sharp increase in reverse current when the reverse bias voltage across the diode becomes excessive. This is also true. To turn a silicon controlled rectifier off, simply remove the gate voltage. No, this is false. We talk of the current there. This is false. In the diagram, the frequency is given. The circuit in fig 1 is operating above resonance. So that is at resonance. Then we are given, in the circuit, the frequency is given. The circuit in fig 1 is operating above resonance. All right, so this circuit that we are given is it operating above resonance given. All right, there we are given 10, and the connection, no, this is wrong. It's supposed to be a parallel combination like this. You're supposed to have a capacitor and an inductor like this. Then we can have a connection there later in parallel, not having this resistor that is there. This is false. It cannot be above. So also at resonance, you must be given what we call the resonant frequency, not the normal frequency. All right, so this is false. Okay, then choose one term from the list of each of the following descriptions and write in the next. Okay, so we're going to choose from these answers. Okay, 1.31. An electronic device with silicon control, that is CRT, the cathode ray tube, sorry. We're given the cathode ray tube as its main component and other associated circuits consisting of a power supply unit, a sawtooth, wave generator, a horizon, and vertical amplifiers. Okay, that is actually a cathode ray oscilloscope. This one, that is the one that we're gonna need. So this was gonna be our answer. Okay, that's 1.31. Okay, then on 1.32, the time duration during which the beam is swept from left to right on a screen of the cathode ray tube by the linearly increasing sawtooth voltage. What is it? That is the sweep time. The sweep time, and we have it here. So there we consider what we call the sweep time. So if we move on 1.33, we're now given an electronic circuit in which the output voltage tracks input voltage both in sign and magnitude. So that will be our voltage follower in that case. So we have to consider what we are given from the to answer these questions. Maximum energy that an electron in a metal is at the absolute zero temperature. If it is at the zero temperature, that is the Fermi level in this case. All right, so there we have got the Fermi level. All right, then the steady flow of electrons in one direction caused by an applied electric field constitutes an electric current. This is the drift current, the definition of a drift current. So that is a drift current there. Okay, so that is what we had. Choose a term from column B that matches the description in column A. So we're going to choose from this, okay? 1.41, the reverse voltage at which a PN junction breaks down with a sudden rise in reverse current. There's a sudden rise in reverse current. All right, that is the breakdown voltage. The breakdown voltage, which is E. So there it was going to be E. The movement of charges from a higher concentration of free charge carriers to a lower concentration of free charge carriers. Okay, this is our diffusion current. And that will be the fusion current. We have got it here, which is I in this case. Okay, 1.43, the time it takes the diode to recover from forward conduction and begin to block reverse current. What is that? That is the reverse recovery current. The reverse recovery current, which is this one on A. So that will be A. 1.44, the minimum current required to hold the silicon controlled rectifier in its conduction state, the minimum, that is the holding current. There we talk of the holding current, so it's gonna be C. When the when the non-supply voltage and current values to a circuit changes momentarily over a short duration of time. They change over a short, that is the transient. Okay, that is G there. All right, so guys, this is your grammar, you know, your English there. So that is what we had on our section A. So if you check section A, we just need to go through your typical topics, each topic by topic. All right, question 2 and 2.1, we are given, this is DC theory and AC theory, the first part being on DC. So we are given this circuit shows a series parallel circuit. So if you had to consider this circuit, this was a wrong presentation, all right? We do understand the current flows from the positive in this way. So in this case, it was gonna be either you correct your currents or you correct your diagram. This was supposed to be the positive, this side, and being the negative. This was a wrong illustration that was presented there. The current flows from the positive side. So according to this flow of current that you're given, this was supposed to be a positive, all right? It flows into this section, branches to this side, another one branches in this, okay? This other section is fine, but that one is supposed to correct how it is presented. So you're asked to answer the following questions using Kirchhoff's laws. Determine the equation for loop A, B, C, F, G, A, okay? That is, if you consider that was first part here. A, B, C, F. Okay, this one, back to the first part. So we are considering this loop here, okay? So let's see how we're gonna formulate this equation from this loop. That is from the given loop A, B, C, F, G, A. All right, so remember that the voltage that we are given in this closed loop is supposed to be equal to the sum of the voltage drop. So we have got a voltage, like I said, this was a wrong presentation, supposed to be positive, negative. So you take it as a positive when it is like this. So 24 is equal to the voltage drop. This current one is affected, if you check between, or it affects resistor 1 and resistor 2 together. So that means we're going to have 20 plus 12. Remember, resistance times the current. So we're going to multiply to I1. You move in this branch C to F. From C to F, we have got a resistor and a current, which is I2. Already the currents are there. So that's resistance and current. So it's going to be 15 times I2. So that's it. 24 is equal to, if you add these two, that was going to be 32 I1 plus 15 I2. So you formed an equation. Just leave it like that. All right, let's consider another loop. Determine the equation of this loop. All right, so let's see what we are given. That is 2.12. So this is from this information, we have to consider the loop A, B, C, D, E, F, G, A. This is what you're given. So if you consider that is A, B, C to D to E to F to G to A, we are moving in the external, in this external way. All right, so we have got a voltage still of 24. So this 24 is equal to the voltage drop from A to C. This one, still the same way that we did previously. We add 20 plus 12 times current 1. Then if we move from C, we're going to combine C, D, E, F, the same current that is flowing here. So we are going to add all these resistors under the same current. That's 28 plus 32 plus 15. This is a single resistor in series. Same current is going to flow. So you multiply to the current, that is I1 minus I2. Okay, then from F to G, we are back to this branch which we had talked about before. So there's nothing to consider there. So this is what we just had. Let us combine. So 24 is equal to 32 I1 plus, if you add these values, you're going to obtain 75 in this case. So this is 75. Then you multiply 75 times I1. That's 75 I1 75 times minus I2, that is 75 I2, like this. So that is, you are going to obtain this equation, add I1 and I1, that's 32 plus 75, that is going to be 107 I1 minus 75 I2. So that's it, you've got your equation. Then from these two equations, calculate the value of the unknown currents I1 and I2. How to calculate these currents? Now it's up to you. You're going to use substitution method, elimination method. That one, it's up to you. So I'm going to consider the first equation. That's 32 I1 plus 15 I2, which is equal to 24. So let's see what we are going to obtain from this one. Then the second one, it was from this side, that is 107 I1 minus 75 I2 is equal to 24. You can also reduce if there is an equation that you can see that this one can be reduced. So like I said, how to solve these equations is actually in your hands. So in this case, I'm going to consider this as my equation 1 and this as my equation 2. So I want to eliminate I1, so I'm going to use elimination method. So in order for me to eliminate current 1, I interchange these values that are on current I1. So 107 multiplies on top. So 107 multiplies everything on top. This 32 multiplies everything below. That is, we can make sure that these two are the same. So 107 multiplies equation 1. That's 107 times 32, which is going to be 32. That's 3424. 3424 I1. 107 times 15, which is going to be 1,605 I2. 107 times 24, which is 2,568. You did the same thing with the 32. It multiplies the 107. That will be 3,424 I1. Do the same thing. 32 multiplies the minus 75. That's 2,400. 32 times 24, which is 768. So as you can see, I1 and I1 is the same. So you can eliminate this by subtracting equation 1 minus equation 2. So if you subtract these two, that will be a 0. You do the same thing, you subtract this minus, it will be a plus. So if you subtract this minus this, it will be a plus. So that will be 4,005 I2 is equal to 2,058 minus 768. That is going to be 1,800. Then we can divide by this 4,005 to obtain current 2. So that's it. We are obtaining I2 in this case, which was going to be 0.449 amps. All right, that is our current 2. With our current 2, we are going to substitute in any of these two equations that we are given. See that we're going to substitute in equation 1 or equation 2. So in this case, if you substitute in equation 1, in place of I2, we are going to have 32 I1 plus 15 times this I2 that we calculated, 0.449. All right, so that is going to be equal to 24. So let's solve this. 32 I1, we take this to the other side. That's going to be a negative on this side. Then whatever that you obtain, divide by this 32, divide by this 32. That is, you're going to obtain current 1, which was going to be 0.5395, which is 54. So it's going to be 0.5395, and so on. So it's going to be 402 to 3 decimal places. Okay, so yeah, let me know how you calculated and the values that you're obtaining. So if you're using the substitution method, it can have some rounded, because you're rounding off these values, they can just get affected a little bit, not that much, but just a little bit. So let's see how you calculated these values. All right, on 2.2, you're given the circuit shows a coil connected in series with a capacitor. So there's a coil resistor and an inductor. Then there's a capacitor. 2.21, calculate the inductive reactance. So that is from our inductor. What is the inductive reactance? XL. So remember, guys, we talked about this from our introduction. XL is equal to 2 pi FL. So there, we're just going to substitute 2 pi times the frequency. We have got the frequency 60, inductance, that is 35 millihenries. 35 times 10 to the exponent of -3. That is our XL in this case, which is the reactance of the inductor. So that was going to be 13,195 ohms. All right, then the capacitive reactance 2.22, that is our XC. So remember, XC from your formula sheet is given 1/2 pi FC. So that's 1/2 pi times the frequency, the capacitance, which is 55 microfarad. That is 55 times 10 to the exponent of -6. So that was going to give us capacitance. But as you know, capacitance in most cases, the reactance. So there's nothing to consider. Sorry for that. Just going to get your answer straightforward. 48,229 ohms. So this is our XC. So we're given the reactance of each. The reactance of that, after that, the impedance. Calculate the impedance. So the impedance, we have to consider between these reactances, because there we have got the reactance of the inductor and that of a capacitor. So remember, I said you must compare these two. So if you compare XC and XL, you were going to see that XC is bigger than 48. It is greater than XL. So therefore, our Z is going to be the square root of R squared plus XC minus XL squared. So if XL was bigger, it was going to be XL minus XC. But in this case, it is XC, which is greater than XL. So that's our resistance, 9 squared plus the difference there, XC minus XL. So that's 48,229 minus 13,195 squared. So you square this, you obtain the impedance of the whole circuit. That was going to be 36,172 ohms. Okay, so there we have got the impedance. Let's see what you are given here. The phase angle. So remember, in a series consideration, I say the phase angle from the resistance and impedance, that is enough for you to obtain this given phase angle. So the phase angle is simply arc cos the resistance over the impedance. So that means arc cos of the resistance, which we are given, remember from our circuit, the resistance was 9, and we calculated our impedance, 36,172. That's our theta. So that was going to be 75,593 degrees. Okay, that's our phase angle in this case. Then the last part, it was now to draw a neat labeled phasor diagram of the circuit. So we have considered, in this case, remember we said XC is greater than XC is greater than XL. So from that, it is more capacitive. So it is more capacitive. You take it in more capacitive because our XC is bigger than XL. If it was or a condition that XL is bigger, then it was going to be more inductive, but this one, it's more capacitive. Remember, a capacitive, you work on this region. So we are going to have our impedance. So you're going to have our XC this side, our XL. Then this is the difference between XC and XL at a certain resistance of 9 ohms that we are given, having our impedance. Remember, we calculated this impedance. I erased it, but that was 36,172. Okay, so that's it. And also consider the current and also write these values XL. Remember, you calculated these values, you write your value, there. You also write your value there if you want to consider that. Okay, but for 3 marks, okay, 4 marks, okay, you can just write those ones, it's fine. Remember, we calculated our XC, it was 48,229 ohms, and this was 13,195 ohms. Okay, so that was it, guys. You have got 4 marks for everything there. On semiconductor diodes and the part of transducers. So in this case, yes, they can combine like that, semiconductors and the transducers at the same time. Then you'll be wondering what is actually happening in that case. So that can be the situation. It can be of that nature. So they were given 3.1 IDC voltages are needed for operation of appliances such as televisions, computers, monitors, computer monitors, and oscilloscopes. Draw a neat labeled circuit diagram of a full wave voltage doubler. So take note there. I want you to draw a full wave voltage doubler. Remember, these are applications of our diodes from the diode application, and it must be a full wave. Okay, so this is what you are gonna have. In this case, I've got this part that I want us to consider. So considering our full wave, let's see what we have in this case. All right. All right, so like I said, guys, these softwares. So this is what we're supposed to have, guys. Make sure that you indicate properly the presentations of your diodes, your D1 and your D2. That is what is most important. So that is okay, that is it, guys. So there we do not even need the end operation, because remember, during the positive half cycle, the diode D1 is gonna be forward biased and conducts current. That is while D2 is gonna be reverse biased and non-conducting and so forth. So, but we are not considering that. We just need the diagram, and in the other half cycle, we will be having D1 reverse biased, whilst D2 is going to be forward biased. So, but in this case, we are not going to consider that. It was just to have the diagram. All right, so let's see the other part, guys, before this software tends to misbehave. 3.2, certain values of the junction capacitance can be controlled in a varactor, which is variable by adjusting the reverse bias voltage. Draw a neat labeled characteristic curve that describes the working of a varactor diode. Okay, remember from our varactor, what is they are saying we need the characteristic curve which describes the operation, not the varactor, but the curve. All right, so remember, on our varactor, this is the characteristic curve that we are going to be having. So that is in terms of what? In terms of the voltage that you are given and the capacitance comparing. So that is what we are given in this case. Remember, when in terms of the operation, we are going to have a condition that the junction capacitance decreases as the reverse bias is increased. It will be decreasing at the same time. So that was it, guys. And the other part, they need you to have the symbol of a varactor. On 3.22, you need the circuit symbol. Remember, this is just a diode with a variable, with that variable capacitor condition like this. So you're gonna have your capacitor here, then you just draw something like that. All right, so that is a varactor, or you can have it this way. Remember, you can have your diode, a normal diode like this, then you indicate the symbol of a capacitor down like this. You indicate a symbol of a capacitor like that. So still, it's fine. Okay, but you must draw neat diagrams, guys. You must have neat diagrams. Okay, optocouplers, which is optoisolators, are used in the industry as single package sensors. Okay, draw a labeled optocoupler using phototransistors as the photo detector, all right, as the photo detector in this case. So that is what we're going to have in this case as a photo detector. That is the input to the diode, that is to the input, the reflected to the transistor on the other part. So that is what they needed in this case. And also 3.41, describe the operating principle of a strain gauge. Considering a strain gauge, what is the operation? So there we have got when the mechanical strain is applied to a strain gauge, the wire or the foil undergoes deformation. This results in the change in its length and cross-section area. It either becomes narrow or longer or shorter and broader. That this causes a change in electrical resistance of the wire or the foil. Or as a result, there is a change in resistance. So guys, do not worry about this because they were given the marker to use dissension when marking your papers, guys. So they are going to consider you as they are marking this part. So do not worry, but make sure that you write what is in line with what is being asked there. Do not just take also this one for granted. To make sure that you do understand the information of what you are being asked there. Make a neat labeled drawing to show the construction of a strain gauge. So there they wanted us to have this construction of a strain gauge. So they're going to consider their different diagrams there. From the one that I'm having, going to have the gauge backing, the resistive foil, which is this part to the strain detection. Then we've got the electrical wire leads, and the solder pads, which are given there. So, okay, that is what we got, guys. And I don't know if you've got another diagram that you were being taught, use that diagram. That is it. Make a labeled drawing showing the construction of a silicon cell under a photovoltaic cells, but it must be of a silicon, cell. All right, so do not confuse that part. So a silicon cell, you're gonna have this of this nature. So these are the part, the p-type silicon base. We're gonna have the back electrical contact, also the PN junction, the N-type silicon. That is the major part that they want you to indicate there. All right, so do not worry about much. Just know the major components that you are given, or that you have, the major components. Those are the ones that you're supposed to just work with. So on the semiconductor transistor and operational amplifiers on 4.1, we are given again a certain information to consider. And from there, we are asked to draw a neat labeled circuit diagram to show a transformer coupling. All right, that's a transformer coupling. So this is what you are needed to have in your syllabus, guys. Make sure that you indicate all the transistors properly for a transistor for this coupling. that we are given, which is our transformer coupling. And that's it for 5 marks. Draw a neat labeled circuit diagram of a series voltage regulator on 4.2. After this information, that's a voltage regulator. It's going to be like this with a Zener diode. So you're going to have something of this nature, the voltage regulated, V in, which is unregulated, then to your transistor. So that's it, guys. Coding to your syllabus, those are the diagrams that they will need you to have. So just make sure you go through, do more question papers so that you get rid of what they need you to answer your questions as. Because at the end of the day, those are the ones that are marking these papers. So if you work your own because you just need your own, it's going to be a problem. Make sure that you work according to what they want you to present your answers. All right, answer the following questions referring to MOSFETs. Draw the IEC symbol of an enhanced P channel MOSFET. That's an enhanced P channel. So that is what we're gonna have for an enhanced P type. Okay, then if in the drain, the subtract, the source, the substrate, sorry, and also the gate. So I think with this, you're gonna obtain your 1 mark. That was just a 1 mark. Then the working principle. On the other part, they need you to describe how that MOSFET, okay, this one they said of N channel, enhanced N channel. The first one was P-type, then this one they want for an N channel. Okay, so considering this, we are given the major part, the current flow in an N-type MOSFET happens because of negatively charged electrons. When a positive voltage is applied with the repulsive force at the gate terminal, the holes present under the oxide layer are pushed downward into the subtrace. That is the substrate. Then the depletion region is populated by the bound negative charges, which are associated with the acceptor atoms. Upon the reach of electrons, the channel is formed. The positive voltage also attracts electrons from the positive N source and drain regions into the channel up to the last part, guys. Just make sure you go through your theory part. All right, so actually you see that is this part of your theory that you need to play around, go through each and every part. In this case, sometimes they give you calculations here and there, but this question paper was just theory throughout. 4.4, it was amplifiers. Answer the following question referring to op amps. 4.41, name 3 advantages of op amp over conventional amplifier. Op amps they have got advantages over the given rational amplifiers. From the size, it has a smaller size, it is more reliable than a conventional amplifier. It costs less due to the types of circuit parts, less power consumption, easy to replace. An op amp can be used for different applications. So that's just any 3 from what you are given there. Then on 4.42, draw the circuit diagram of an inverting amplifier. Op amp, remember, working with our op amps, you're supposed to know each and every type. So there they need us to indicate of an inverting op amp. So that's from our inverting op amp. That is what you will need. So like I said, you must know each and every diagram. They're gonna ask any diagram from there. Explain the purpose of a voltage follow amplifier, that is a voltage follower. What is it that you consider on a voltage follower? So voltage followers are considered to have high input impedance and low output impedance. This is the essence of their buffering action. They strengthen a signal and thereby allow high impedance source to drive at low impedance load. So that is what was enough in this case to answer this question. The input of integrator of amp is a sinus wave, that is a sine wave. Draw the output wave of integrator. The input is a sine. What about the output, how it is gonna be given? So it's just gonna follow suit the input, but just being a stretch like a cos, the opposite, just like you remember the graph of a cos. So this is the opposite of a sine on the output. So the input is a sine, the output is that shape of f cos. That is what we needed in this case for 2 marks. I think, guys, it's enough for you to just present that way. The measuring instruments and electronic power control. With this information, draw a labeled circuit diagram of a frequency counter. That's a frequency counter. How does it look like? So a frequency counter, remember, this is just a series connection of this amplifier, Smith trigger, and the counter connected to the unit display. And also do not forget the time-based generator. That is what we are given. With that, guys, you can obtain those marks that you are given. Then we are given this diagram shows the block diagram of an oscilloscope. From this information, explain the purpose of the deflection plates on the oscilloscope. What is the purpose of the deflection plates on our oscilloscope? That is the what you needed there. Okay, just 2 marks. So we have got a lot of things to consider. I don't know which part are you going to consider. You can consider the vertical deflection plate turns the ray up and down, and the horizontal ray moves the electron beams from left side to the right side, or you can consider any of these two that you are given to indicate the purpose of the deflection plates. All right, then the other part, it is the purpose of the time-based generator. What are you going to need the time-based generator for in this oscilloscope that you are given? So that is also important to know. So it is used, the time-based generators produce very high frequency sawtooth waves specifically designed to deflect the beam of the cathode ray tube smoothly across the face of the tube and then return it to the starting position. So guys, also like I said before, these guys, they are going to consider you, but make sure that you write something that has got sense of the diagram or what you are working with, so that also they consider your answers. Okay. A silicon-controlled rectifier is a 4-layer solid-state current device. We know that. Draw a neat labeled characteristic curve, guys. Describe the operation thereafter of this, okay? So we've got 2 things. The second, the characteristic curve. Remember, a silicon-controlled rectifier, that's what you're going to have, the reverse breakdown region and the forward conduction region. And the operation thereafter, we are gonna consider this when the voltage is applied across the thyristor, no current flows because neither the transistor is conducting, and as a result, there is no complete path across the device. If a small current is passed through, we are going to see through the gate electrode, this will turn transistor 2 from what we are having here. All right, how can I go back here? But just here, it's gonna turn this one, okay? Then And that is, okay, the cathode of the whole device, that is the cathode of whole device. When this occurs, it will cause the current to flow through the base of transistor 1 and 10, that transistor on, and so on until this will cause the current flow in the emitter of TR2, transistor 2, causing its on state to be maintained. In this way, it only requires a small trigger pulse on the gate to return the thyristor on. Once switched on, the thyristor can only be turned off by removing the supply voltage. So that's what you are required to describe in that case. So just make sure you go through your theory. That is 5.4. In a full wave control, with this information, draw a labeled circuit diagram of a full wave control circuit using the back-to-back method with the two silicon controlled rectifiers and the two control circuits. So there must be two silicon controlled rectifiers and also the control circuits according to what we are given. So this is the diagram that they want you to have at the end. There was silicon controlled here and our control circuit control 1 and control 2 to the load. So that is for 3 marks. And also the last part, which was to draw the circuit diagram to show how forced commutation is achieved. A diagram to show how a forced commutation is achieved. You're gonna have our transistor with the silicon controlled rectifier power and so on. So that is what we needed. So make sure you study your diagrams, do understand your diagrams, work with your diagrams as much as you can. That can help in these revisions. And also your theory part is important as you are working. As you can see, part of theory is important. Actually, it carries a lot of marks, the calculations here and there. So yeah, let's revise as much questions as we can. Just do more question papers so that you see how do they ask these typical questions on your industrial electronics N3.